So hello everyone, welcome you all at Lokesh Limited Study Zone. So we're starting our chapter here, continuing the lecture number 2, magnetism, moving charge and magnetism. Okay, yes, in yesterday's class, we have derived the numerical for the intensity of a magnetic field axis on the axis of a circular loop. Okay, over there we have seen a very important derivation is there, that is mu 0 upon 4 pi 2 pi a square I a square plus x square whole to the power 3 by 2. Clear? So if there are n terms, then the amount of magnetic field or magnetic induction or magnetic field intensity is given by mu naught upon 4 pi 2 pi n I a square plus x square whole to the power 3 by 2. So please, I ask you once again to write this uh, result. What is B? B equals to B on the axis. Okay, it is on the axis. B equals to mu naught upon 4 pi 2 pi n I a square into 2 pi n I a square whole divided by x square plus a square or a square plus x square to the power 3 by 2. X square plus a square whole to the power 3 by 2. Correct? We have this relation. From this relation, many type of question were asked. So see what type of questions may be there. First case, if you're talking about center, okay, if you're talking about center of the magnetic loop. Now, one more thing, the magnetic intensity is working along x-axis. In the derivation, we have seen that this vector, final vector is propagating through here. So if you place a vector sign here, then the direction of the vector is along I cap, right? Yes. At center, for center of the loop, at center of loop, what you have to do, place x equal to 0. Clear, beta? So watch carefully. Be at center. At the center of loop, you will get the same result. Mu naught upon 4 pi. Here it is 2 pi I a square. Now this x becomes 0. So 0 plus a square equals to a square whole to the power 3 by 2. So 2 and 2 get cancelled out and here it will be a cube. Got it? Now a square 2 power will be cancelled and here it will be, sorry, it is 2 pi. It has to be 2 pi and n should be there. Okay. So this will be mu naught upon 4 pi 2 pi n I upon a. Clear? Here a is the radius. In our previous derivation, when we have directly derived this derivation of circular loop, so we have got the formula like this, mu naught I upon 2r. Okay, there was n equals to 1. As we have derived it only for one terms, so if you can more simplified it, so 2 pi and 4 pi will cancel up to 2 times. So mu naught ni upon 2a. Okay, so for a equals to r, if you considering r in the place of a, so your derivation will be mu naught ni upon 2r. Clear? So you see this is the same result that you are proven, okay, for the case of center of the magnetic center of the circular loop. Clear? Yes, we have already proved this one. Yes. So if take n equals to 1, then for single loop, b equals to mu naught I upon 2r. Yes. Second thing, case number 2. When radius of the dipole is very small, sorry, radius of the loop, when r small r is very small, okay, then what happened? R square plus x square plus r means here we have in the place of a, we already have taken a, so we have to go with a only. A square plus x square is nearly about a square. Okay, wrong it is, my dear. It should be x square. Yes. So a square plus x square equal to x square. Clear? Yes. You see, when the radius of the loop is very small, this means in comparison to x, when a is very, very small, okay? So you can eliminate a, or you can say you can neglect a, okay, with comparison to x, and there will be only x square, okay? So coming to the value of derivation, b on the axis equals to mu naught upon 4 pi 2 pi n I a square. Now eliminate the a square, and here x square plus a square, it is become only x square whole to the power 3 by 2, right? Hmm. So yes, check here. Correct. So 2 pi n I a square x square whole to the power 3 by 2. Clear, beta? Now 2 से 2 cancel, 2 and 2 cancel. Now it will be b axis equals to mu naught upon 4 pi 2 pi n I a square upon x cube. Now see here, what is magnetic moment? For a circular loop, magnetic moment is equals to I a. Yes or no? Yes, we have read it in the previous chapter. Magnetic moment equals to I a, and for n terms it should be n I a, right? So m equals to n means n's, I means I, and for a you can write pi a square because circular loop having the area pi r square, but here the radius is a, so it has to be pi a square. Clear or not clear? So n I a square in the place of n I a square. Sorry, pi is also there. So n I pi a square. This whole terms will give a capital M. Yes or no? And 2 cancel here, or you not need to cancel it, sorry. 4 pi, and this is 2. So b axis equals to mu naught upon 4 pi and into multiply by 2m upon x cube. Clear or not clear? And for vector, if you place a vector here, then the direction should be in accordance with the I cap. Clear? A great observation is there. Do you know this result is same result that you have obtained for the axial condition, result for the axial condition at a distance x from the center of the loop. Yes or no? Center of the magnet here, point P. So what was the result in axial condition at point P equals to mu naught upon 4 pi into 2m upon x cube. Understood? This means This means a magnetic loop, a circular coil. Okay, for a distant point, a circular coil behaves like a bar magnet. Yes or no? You're having the same axial magnetism for both the combinations, both the configurations, a bar magnet and a circular coil. So it behave like as a bar magnet. Okay. So a question is there in the CBXC examination that explain how a circular coil behave as a bar magnet. Okay. So we have to derive this result in accordance with the magnetic dipole moment of a circular coil. Clear? Okay. So noted down. Noted, Nitin. This was the same case for what I am talking about. When point P lies far away from the center of the coil and x is very, very greater than A, so it is equals to pi a square eliminated, and it is equals to 2m upon x cube. Clear? So it's same as for bar magnet. Clear? magnet. Now, next concept, numericals are homework here. Okay, all the three numericals, three or four numericals as homework. So only derivation for result for um, magnetic field due to a straight wire carrying current. Make a heading, magnetic field due to a straight wire carrying current. So there is a straight wire carrying current I, and you have to find the magnetic field. So as same, place your thumb here along the direction of current, and you will see your wrist part will be lying here. This means lines of forces are moving inside. So the direction of magnetic field will be inside, perpendicular to the plane inside, and this side it will be out of the plane. Clear? Now, to find the direction, to find the intensity of magnetic field, write this one formula. B is equals to mu naught I upon 4 pi A sine phi 1 plus sine phi 2. Sine phi 1 plus sine phi 2. Okay? Mu naught I upon 4 pi A sine phi 1 plus sine phi 2. Yes, beta? For infinite, for current carrying conductor, straight current carrying conductor, straight current carrying conductor. Okay. So there is a straight current carrying conductor. From some point, the perpendicular distance of the observatory point to investigation is A. This is the point of investigation to find the magnetic field intensity at this point. Okay. If this one angle is phi 1 and another, this one angle is phi 2, then the intensity of magnetic field is given by B equals to mu naught I upon 4 pi A. Look here, the two angles are there. One is phi 1 and phi 2. Okay. And this one angle is phi 1 and the above one angle is phi 2. Okay, no matters which one is phi 1 and phi 2, but here B is equals to mu naught I upon 4 pi A sine phi 1 plus sine phi 2, right? This is the derivation to calculate the magnetic field intensity at a given point, okay, at a distance A. Now, special cases are there when you have infinite conductor. Now, students, see here, when the length of the conductor it goes to infinite, if the length of conductor goes to infinite, you can understand that this angle will be rapidly increases. Yes or no? So can you say that when the length of the top and bottom part goes to infinity, this angle is nearly equal to 90 degree? Yes or no? Confirm or not confirm? Yes. So here the angle equals to, for infinite length, phi 1 equals to phi 2 equals to pi by 2. Clear, beta? So we can place here in the place of phi 1 pi by 2 and phi 2 pi by 2. Pi by 2 means 90 degree and sine 90 degree equals to 1. So 1 plus 1 equals to 2. So B equal to mu naught I upon 4 pi A multiplied by 2. 2 cancel 2 times. So answer equal to mu naught I upon 2 pi A. Clear? So this is very important derivation. Okay. And this is the derivation for magnetic field for a infinite conductor. Yes. Mu naught upon 4 pi, mu naught upon for I, mu naught I upon 2 pi A. So more better you can write this one mu naught I upon 2 pi A like this. See here. If you place here mu naught upon 4 pi means you have to multiply 2 at the numerator. So it will be 2I upon A. Clear or not? So write this one formula B equals to mu naught I upon 4 pi 2I upon A. Same result is here. Okay. Yes. Yes, and another interesting case is also there. When the conductor xy of infinite length, but the point P lies near the end y. You see here, this is the point at a distance A. This part goes up to infinity. Clear? This means the angle phi 2 is equals to pi by 2 because it is up to infinite, and angle phi 1 equal to 0 degree. Why? Because the bottom part of the conductor is just near the point P. Okay. See here in the original diagram, there was two angle phi 2 and phi 1. So phi 2 is here continuously increasing. So it goes up to 90 degree. Phi 2 is equals to 90 degree. But this part is continuously, the one end of the conductor is nearer the point P. So this angle continuously decreasing, and when this end comes closer to this point P, so phi 1 is equals to 0 degree. Clear or not clear? So phi 1 equal to 0 degree. So place here phi 1 equal to 0 degree. Sorry, phi 1 equal to 90 and phi 2 equal to 0. Clear? So phi 1 equals to 90 degree. The upper angle is phi 1. So phi 1 equals to 90 and phi 2 equals to 0. So answer mu naught upon 4 pi a sine 90 plus sine 0. Sine 0 becomes 0 and sine 90 equal to 1. So your answer equal to mu naught I upon 4 pi a. Clear? Yes. So only two results are useful to us. First, mu naught I upon 2 pi a. If you solve this, you will get mu naught I upon 2 pi a. Okay. For infinite length conductor, and for, if the conductor xy of infinite length, but the point P lies near the end y or x. Okay. Any one end, if your point is lying near that point, then B equals to mu naught I upon 4 pi a. Clear? Now, direction of magnetic field. So yesterday I have told you to how to identify the direction of magnetic field. So just hold the current in the direction of thumb and just curl your fingers. So the way your fingers will curl in the same direction, your magnetic field will be there. Clear? Yes. So here magnetic field is like this. Okay. So from front side, magnetic field will go inside the plane of paper, it will go forward. Okay, like your conductor is downward, then place your thumb like this, and you see your fingers will curl like this. Okay, so this is the direction of magnetic field. Clear? Towards your wrist, where is your wrist means towards the wrist area, the field will be crossing the plane of paper. Okay, so field will be getting inside into the paper, and towards your fingers your field will be outward. Okay, okay. So if we imagine the linear wire conductor to be held in the grip of the right hand so that the thumb point in the direction of current, then the curvature of the fingers then the curvature of the finger around the conductor will represent the direction of magnetic lines. Done. So our next topics for today is Biot-Savart law. Biot-Savart law, sorry, it's not Biot-Savart law, Ampere's law and its application. Okay. And by using Ampere's law, we have to derive the magnetic field intensity using infinitely long straight wire. We just find the intensity of infinitely long wire is mu naught 2 pi upon r. Sorry, mu naught I upon 2 pi r. Yes or no? Mu naught I upon 2 pi r. But we have to find this intensity now by using Ampere's law. It is called Ampere-Circuital law. Okay. So write the heading, guys, Ampere-Circuital law. Ampere-Circuital law. Ampere circuital law, the definition of Ampere circuital law is B dot dl equals to mu naught I enclosed or I total. Okay. Yes. I net. Yes. What does integration mean? Integration dl means integration of magnetic field along the length. This is called line integral of this part is called line integral of magnetic field intensity. Okay. This whole part is called, left part is called line integral of magnetic field intensity. Magnetic field intensity over a closed loop. Over a closed loop. Okay. This loop is called Amperian loop. Like there in the electricity, the surface was called Gaussian surface. Here, this imaginary loop is called Amperian loop. Amperian loop. So, the total line integration of magnetic field over a Amperian loop means what? You add all the magnetic intensities values over a closed loop, and this is equals to, this integration is equal to mu naught times the current threading through the loop. Current threading through the loop means the amount of current passing through that loop. Okay. So if there are like 2 ampere and 1 ampere current is threading from the loop, so here it will be 3 ampere inside the I net bracket. Here there will be 3. So 2 ampere plus 1 ampere, the total amount of current I net equals to 3 ampere. Clear? For example, I have taken the two currents are threading from the loop. Okay, so the total current equals to 3 ampere. Okay, so this is called Ampere circuital law. Yes, Ampere circuital law. It states that the line integral of the magnetic field B, yes, line integral of magnetic field B around any closed path in a vacuum is equal to the mu naught times the total current I threading the closed path. Yeah, threading the closed path, or you can say threading the closed loop. Clear? Yes, this is the statement for Ampere circuital law. It states that the line integral of the magnetic field B, okay, and as the loop was closed, so you have to use a sign here. This one, this is for the closed loop. This integration is for closed loop. Okay. When you integrate through an open loop, you need to only place this one sign. But you have a closed loop, then you have to place a 0 over the integral sign. So this is for closed loop. For which quantity integration? The integration of magnetic field over what? Over the length dl, okay, equals to mu naught multiplied by all the current threading through that loop. You can say I net. Okay. Now, proof of Gauss law, sorry, Ampere circuital law. Okay. We are going to prove the Ampere circuital law. Ampere circuital law. Yes. Consider we have a straight conductor. Consider we have a straight conductor. This one. Okay. And because of that, at a distance is small r, there is a magnetic field. Yes, magnetic field like this. Okay. Yes. We also have calculated at this point the magnetic field intensity will be outward into the plane. Yes, outward, not inside to the plane. Okay. This is current I. So this is the Amperian loop for what we are talking. This is the Amperian loop, as there is a value of B is constant. The magnitude of B is constant everywhere, right? Okay. So we have to prove what? We have to prove integration of B dot dl equals to mu naught I. So taking LHS equals to integration of B dot dl. Clear? Now, what is the intensity of magnetic field for a circular loop at a point R? We also have calculated that B vector is equals to mu naught I upon 2R. Yes or no? The magnitude of B vector equals to mu naught I upon 2R. Clear or not clear? So, first open a dot product by A dot B equals to mod A mod B cos theta. Clear? Now see here it is equals to mod B mod dl and cos theta becomes 0 degree. Why? You see at this part the dl length vector, very small length vector, is just axial in the direction of magnetic field because magnetic field is going into the plane. Yes or no? In the same direction this length vector is going because here the direction of current element, sorry, not current element, the direction of magnetic field will be according to the length vector. Clear? So see here, this is the length vector and in the same direction magnetic field is propagating inside. Yes or no? So the angle equal to 0 degree cos theta, it becomes cos 0. Clear? Now B, place the value of B here. What is B? B equals to mu naught I upon 2R. DL means DL and cos 0 equal to 1. Right? So mu naught I upon 2R inside the bracket DL. DL means the integration of length vector. So when there is a circular loop of vector, so when there is a circular loop of radius R, then the total length of the loop will give you the total integration length integral equals to 2 pi R. Yes or no? The total length becomes 2 pi R. So mu naught I upon 2R multiplied by 2 pi R. Clear? 2R, 2 pi R upon 2R. So this is equals to 2 pi R. Mu naught I upon 2R. Yes, 2R get cancelled. One more pi should be there. B equals to mu naught I upon 2 pi R. Sorry, students, a mistake is there. We have to place the value of B is equals to, for a circular loop, it was mu naught I upon 2 pi R. Yesterday we have derived that mu naught I upon 2 pi R. Clear? So it was 2 pi R. For a straight conductor, it is mu naught I upon 2 R. Okay, for a straight conductor at a point, it is equals to mu naught I upon 2 R. But for a circular loop, it is equals to mu naught I upon 2 pi R. Clear? So mu naught I upon 2 pi R. B equals to mu naught I upon 2 pi R. Here it is also 2 pi R. 2 pi R. Now 2 pi and 2 pi get cancelled. Clear? R is also cancelled. R's to R cancel. So B dot dl integration of B dot dl equals to what? Mu naught times of I. Yes or no? So this is the proof for Ampere circuital law. Okay. Yes, let us check it once again in a systematic way. Proof. Consider a long thin straight wire XY conductor carrying a current I. The magnetic field around the conductor are concentric circle in the plane perpendicular to the wire XY. So here the magnitude of magnetic field produced at point P, we have considered any point P on the Amperian loop passing through this. Okay. So this is the point P and point P Amperian loop passing through this. So the direction of magnetic field here will be cross vector, you can say. inside the plane of the paper, right? And in the same direction, dl vector means length component vector will moving. Now the direction of the magnitude of magnetic field is given by B equal to mu naught upon 4 pi 2 I upon r, that is equals to mu naught I upon 2 pi r. Clear? So this is the magnetic field at that point. The direction of B vector is along the tangent of the magnetic field. Everyone knows that the direction of magnetic field is given by the tangent of the magnetic field. Yes or no? At any point. So here the consider a circular closed path. Yes, this is an Amperian loop. Okay, we have considered an Amperian loop. And remember, Amperian loop always pass through where you want to find the magnetic field intensity. Okay, there may be a number of Amperian loop, but your interest is here to find the magnetic field at point P. So you have to consider your Amperian loop passing through that point. So consider a closed circular closed path of radius r whose center O lie on the straight current conductor. Take a small element of length dl at the closed path at point P. The direction of B and dl are the same. Understood? So you can say the vector B is parallel to the vector dl. So the angle between B and dl equals to 0 degree, right? So therefore the integral of B around the closed path of radius r equals to given by B dot dl equals to B dl cos 0. Clear? B dot dl equal to mod A mod B cos theta. So B dl cos 0. So integration B dl. So B outside the integration sign as it was constant into integration of dl. dl is the full length vector. So place the value of B dot dl here. In the place of B, here it is equals to mu naught I upon 2 pi r and the length vector integration equals to 2 pi r. 2 pi r get cancelled out and will produce you B dot dl equals to mu naught into I. Right? So this is the magnetic field. Sorry, this is the proof of Ampere circuital law. Okay? Yes. Okay, so next is its application to infinitely long straight wire. So now we have to find the magnetic field intensity because of an infinitely long straight wire using Ampere circuital law. Okay, so right, next topic, intensity of magnetic field due to an infinitely long straight wire. Okay, so magnetic field due to a current carrying conductor through a very long circular cylinder, or you can say infinitely long straight wire. It is same for infinitely long straight wire. Clear? So three cases may be there if you considering here circular cylinder. But if we talk about infinitely long straight wire, infinitely long straight wire. So what we are going, we have to find the magnetic field intensity. Okay, we are going to find the amplitude or sorry magnitude of magnetic field intensity as well as direction. So first we have a infinitely long straight wire. Remember, we already have found the intensity of magnetic field here of due to a infinitely long straight conductor, that was mu naught I upon 2r. Okay, the same result we are going to develop here, but using Ampere circuital law. You will see the same result we will have. Okay, so there is an infinitely long straight conductor, and we have to find the intensity at a point r, at a distance r from the wire, right? So at a distance r, there is a point P. There is a point P. Consider there is a point P. We have to find the intensity of magnetic field. We know that because of a straight wire, the magnetic field intensity pattern is like a concentric circle. Yes or no? So consider a Amperian loop. You have to write this line that consider a Amperian loop passing through point P. Okay. Consider an Amperian loop. Okay. What type of loop it is? Circular loop. Consider an Amperian circular loop passing through point P. Yes, I said that where you want to find the magnetic field intensity, that point should be in the loop. Okay, that point should be lying on that loop. Okay, or your loop should be passing through that point. Only then you can find your magnetic field intensity. Clear, beta? So, guys, this is our point P where I have to find the loop. Now, see at this point, magnetic field be radiated perpendicularly inward. Yes, here it is. It will be the direction of magnetic field, right? And the direction of magnetic loop, yes, this loop is also along this. So the same direction dl having, yes or no? Now I can write by Ampere's circuital law. Ampere circuital law. Ampere circuital law, we have a statement that line integral of the magnetic field. So this is magnetic field and line integral means dl. So B dot dl equals to mu naught and current I. So you have given the threading current, only one circular conductor is there. So that having the current I. Yes or no? Hello. So as there is only one conductor having the current I, so we have placed mu naught I. Now the value of B as so first always solve this one. B dot dl, B dot dl equals to mod of first vector, that is B, mod of second vector, that is dl, and cos 0 degree. Yes or no? So cos 0 become 1, it is equals to B into dl. So capital B into dl, line integral, whole integral is equals to mu naught I. Right, beta? So now B is constant everywhere, as the magnitude of magnetic field will be constant everywhere because all the points are at same radius r. Yes or no? So everywhere the magnitude of magnetic field will be constant. Only dl will going to be integrate equals to mu naught I. Right? So B equals to here dl. The integration is equals to 2 pi r. Right? Equals to mu naught I. So B equals to mu naught I upon 2 pi r. Clear? So this is the magnetic field because of a straight infinite conductor mu naught I upon 2 pi r. Okay? Yes. So remember, for a circular loop, circular carrying current, the magnetic field at the center was B center equal to mu naught I upon 2r. And due to an infinitely long conductor, it is equals to mu naught I upon 2 pi r. Okay? Only difference of pi is there. Clear? So answer here B equals to mu naught I upon 2 pi r. Clear? Note it. So this is the derivation for magnetic field intensity due to infinitely long conductor. Okay. You see it was mu naught I upon 2 pi r. Yes, we have also developed this by using Biot-Savart law earlier in the class. And it was mu naught I upon 2 pi a. As a was the radius there or a was the distance is there. But here r is the distance. So it will be mu naught I upon 2 pi r. Clear? Yes. So write it this one. Students, remember when we talking thin conductor, it means there is a breadth-less conductor. Like here, we have considered a conductor is very thin. So you have to consider the breadth of the conductor is like 0. Clear? Only length component is there, like a thread. But in some cases, you have asked there is a cylinder, magnetic field due to cylinder. So there will be some breadth in a cylinder. Okay. Yes or no? Yes, there will be some breadth. There will be some area of cylinder like this one. This cylinder having length as well as this cylinder having the length as well as there is a cross-sectional area, means some material area is there. Okay. So one question is there, a current is flowing through this circular cylindrical section, and you have to find the magnetic field intensity on the three region. First, consider this is as axis of the cylinder, right? So you have to given 3 points upon which you have to find the magnetic field intensity using a pair circuital of first your point is outside this section. Okay. So your point is here. Consider this point as point A because we have to find the magnetic field at point A. Clear? If you're taking the radius of the cylinder is equals to R, and this radius is small r, BA means when your radius is outside the, your distance of your point is outside the cylinder radius, right? So in first case, the distance from the point is greater than your radius of the cylinder. Clear? Second case, B at point, you can take it point is small c. So B at point C means R equals to capital R. Second case, right? And third case, here inside the cylindrical body means you have to find the magnetic field intensity here at this point. I'm marking this as red color. You see here. So B, name of this point is P. Okay. So third point is magnetic field intensity at P. And definitely here radius of this point is lesser than capital R. Okay. So student, I am going to derive the general cases for all the situations. First, your point is lying outside the cylinder as the radius of the cylinder radius, as the radius of the cylinder is capital R. So if your point is lying outside the cylinder, then distance will be greater than R, right? Second case, your point is lying on the cylinder, on the surface of cylinder, then this is your point C. So your radius of the distance of the point is equal to radius of the cylinder. And if your point lying somewhere inside the cylinder, then distance is less than capital R. Understood? So we have to derive the three cases. Three cases are very important. So let us derive the three cases. Okay. So the same derivation is here. Magnetic field due to a current conductor. Magnetic field due to a current through a very long circular cylinder. So you have a circular cylinder having some area, okay? It having some thickness. Clear? Okay. Consider an infinitely long cylinder. So you have an infinitely long cylinder that it is moving plus infinite upside and minus infinitely downside. This is a very long conductor, okay? Consider an infinitely long cylinder of radius capital R. So if having radius means it having some diameter, obviously some thickness will be there. With axis XY, the current I be the current passing through the cylinder. The magnetic field lines of forces are perpendicular to the length of cylinder. Obviously, you know, so magnetic field lines are always perpendicular to the plane of current conductor. So the magnetic lines of forces will be perpendicular to the plane of cylinder, right? Okay. So this is the Amperian loop. Later on, we will take this. But one more thing, you remember, like when you flow a current through a cylinder, important line, remember students, when you flow a current like I ampere you are flowing through a cylinder, then this current will be carried out the cylinder by its whole cross section area. Okay. This means current is not only flowing through any one point. It is flowing through whole of the cross section area. Clear? Okay. So this means current will carry through full cross-sectional area. Okay, this concept will be incorporated here later on. See, so first case. First case is when point P is lying outside the cylinder. So we are deriving this case when point P is lying outside the cylinder. So let R be the perpendicular distance of a point P from the axis of the cylinder. So consider the distance of this point from the cylinder, center of the cylinder is equal to small r for the first case. Clear? Hmm. So let R be the perpendicular distance of the point P from the axis of cylinder, and capital R is the radius of the cylinder. Yes, capital R is the complete radius of the cylinder. Okay. In first case, a small r is greater than capital R, means observation point is outside of the cylinder. Okay. So you have to consider a point P, and that point P pass a Amperian loop. You will have the magnetic field inside the plane of paper, and along the same direction the length vector dl will be there. So the r be the radius of the perpendicular distance of the point P from the axis of the cylinder, where small r is greater than r, means r is outside the cylinder, point P is outside the cylinder. The magnetic field P is acting tangential to the magnetic lines of forces P. So B and dl will be in the same direction, or you can say B vector is parallel to dl, right? So by the Ampere circuital law, B dot dl is equals to mu naught I. So B dot dl, B is outside again and dl inside the integration sign. Now integration dl is equals to 2 pi small r. Remember, this is not a capital R. This is the length of this one loop, 2 pi r small r. Clear or not clear? So 2 pi is smaller. So B equal to mu naught I upon 2 pi r. So B is inversely proportional to R. As mu naught and 2 pi are constant, I is also constant. So B is inversely proportional to R. Clear? Remember the first Oersted experiment. I told you, as you increase the value of R, as you increase the distance from the conductor, your magnetic field will be decreases. Clear? So same result is obtaining here. B is inversely proportional to R. And this is the first derivation when your point is outside the cylinder. Clear? Second point, your point of observation on the cylinder. Yes, second case when a small r. So second case is taken here is small less than r. Okay. Point P is lying its inside cylinder. So see, r is less than r. And third, r is less than r. Here it is given r is less than r. And second, hmm, yes, yes. So I have to take the case first when a small r is equals to r. Okay, small r equals to r. So what place here is small r equals to r. Case number two, I am deriving here. Case number two, when a small r equals to r. So place the value here b on the surface. So B on the surface equals to mu naught I upon 2 pi capital R. Understood? Mu naught I upon 2 pi capital R. Why? Because your Amperian loop will be passing through here. So this is the second case. I am making this one by orange pen. So if your point will be here, then your loop will be here. So your derivation will be like this. B dot dl is equals to mu naught into total current threading is I. So B is outside, dl inside becomes this equals to mu naught I. So B into integration of dl becomes what? 2 pi capital R. My dear, now point P is on the surface. So you will have to take the full radius. Clear? Okay, capital R. So equals to mu naught I. So B equals to mu naught I upon 2 pi capital R. Clear? Understood? Yes. Next point. Third, when P point is lying inside the cylinder. we may have two possibilities. If the current is only along the surface of the cylinder, which is so the conductor is cylinder is a sheet of metal, then the current through the closed path L is zero using the ampere circuit law. Try to understand this. See here. What is happening here? This is our conductor. Okay, beta. This is our conductor, and this conductor is made up of metal, right? Metallic cylinder is there. And as I said, during a case of metallic cylinder, all the current is passing through the surface. Okay, not a single amount of current passing through any inner part, or you can say volume. Only whole the current is passing through the surface, right? And you have to find the magnetic field intensity here at this point. Your point of observation is like here. Okay. Question is to find the magnetic field at point P. So what you have to do? You have to consider the same Amperian surface. So you have considered a same Amperian loop here from P. Okay. And applying the Ampere circuital law. So by applying the Ampere circuital law, B dot dl equals to mu naught multiply by I enclosed. Okay, beta. So B will be come outside because the magnetic field will be same everywhere and dl will be here mu naught. Now tell me, does there any current inside the volume of the conductor? Yes or no? Yes. What yes? Does there any current inside the volume of the conductor? All the current is passing through the surface. So does there any amount of current threading here from this surface? See here, I said all the current is passing through the surface. Okay. All the current is passing through the surface means outer boundary. There is no current inside the conductor. All the current is passing through the surface only. Okay. As this is metal. Okay. There is no current inside the volume of the conductor. Clear? So mu naught I enclosed here equal to 0. Clear? So B equals to what? 0. Understood? So you have been given a metallic conductor, metallic rod of any thickness, and question is asked to find the intensity of magnetic field inside this rod. Okay, answer B equal to 0. There is no magnetism inside the material of the rod. Clear? So B equal to 0. So same case is mentioned over here that B equal to 0. Clear? Yes, second case, if the current is uniformly distributed throughout the cross section of the conductor, then the current of closed path L is given by. Okay. If the current is uniformly distributed through the cross section of the conductor, it means now you have been given a case that whole the current is passing through whole cross section. Clear? Like so. What? See here. You have given this one conductor. This is full conductor. Okay. Okay. Full conductor having radius capital R. Now case 2 is given. Case number 2. So the current is passing through whole the surface area. This complete surface area is utilized to passing the current. And you have to find the magnetic field intensity at this point, say small r. Here is your point of observation at a distance r. Clear? So see, your current amount is I. So by the whole area, total area is pi r square. So your circular cross section is pi r square. Pi r square utilized how much current? I current, right? Pi r square utilized I current. The area pi r square flowing a current I. So unit area will flow a current of pi r square. Sorry. I divided by pi r square. Okay. I divided by pi r square. Once again, if pi r square area utilize the current I, then unit area will utilize the current of I upon pi r square, right? So the r radius, so this r radius area will be pi is small r square. Yes or no? So if unit area conveys the current of I upon pi r square, then the pi small r square area will convey a current of I upon pi capital R square multiplied by pi r square, right? Pi to pi cancel. So the current from this cross section is given by I equals to I dash. You suppose I dash or I enclosed. Okay, I enclosed. But because our Amperian loop is only this one, so we have to find the current flowing through or a threading through only this section. Okay, we have no need of the whole current. Whole current from the full cross section is capital I know, but we have to find the current passing through only this section of radius small r, and that current I dash, or you can say I enclosed, is equals to how much? That is equals to I small r square upon capital R square. Clear? Okay. Now using Ampere circuital law, by Ampere circuital law. What? B dot dl integration B dot dl equals to mu naught multiplied by I. My dear, it should be here I dash. Okay, because the enclosed current through this section is not I, rather it is I dash. Yes or no? So B dot dl, again same process will be here. Mod A, mod B, cos theta, 0 degree angle will be here, and mu dot into I dash. Place the value of I here. It is equals to I r square upon capital R square, right? Now B take outside, dl become integration of dl, and cos 0 become 1. So no need to write that. Mu naught I capital I small r square upon capital R square. Okay. So place the value of dl here. So dl is equals to 2 pi r. B into 2 pi. What it should be? Small r or capital R? Say dl, integration of dl. It should be small r or capital R. The radius of the Amperian loop we have considered equal to small r. Okay. So it should be small r. Okay. So 2 pi r equals to mu naught I capital R square upon R square. Clear? So B equals to mu naught I small r square upon 2 pi small r into capital R square. Now R cancel. Okay. So it is equals to mu naught I upon 2 pi r square into capital R. Sorry, into small r. Getting? Now you see this whole is constant. Everything is constant. Mu naught upon 2 pi is constant. I is constant. R square. So B is proportional to R. Okay. So what we have seen? We have seen as a combined graph. We seen for a conductor, cylindrical conductor. We have seen two things. If this is made up of metal, if this is made up of metal, then what is the variation of magnetic field? See here, by interesting diagram. Yes, I am showing the diagram B versus R, magnetic field versus R. So along this is magnetic field and versus radius. Clear? See, up to till you are inside the metallic conductor, till you are inside the metallic conductor, your intensity will be equal to 0 up to this point. Okay. Here up to this, your magnetic field equal to 0. Clear? But when you touched the boundary, a small r, your small r becomes capital R. Suddenly your magnetic field rises. Okay, to the maximum value. This is B at R. Okay, we have already developed this one. See here, this is B at R. Second case, case number two. Okay, B at R. Hmm. So B at R, what it will be? Mu naught I upon 2 pi R. Mu naught I upon 2 pi capital R. Clear? Mu naught I upon 2 pi capital R. Yes. And then if you're going outside the loop, your intensity will be here inversely varying with respect to radius. B is inversely proportional to R because C, when you are outside the loop, here, check here. When you are outside the loop, we have derived B equals to mu naught I upon 2 pi R means B is inversely proportional to R. Yes or no? Yes. So this type of variation is there till you are inside the loop. Okay. Till you are inside the loop, there is a intensity is 0 for a metallic conductor. Intensity is 0. When you are just at the surface, then your value will be maximum on the surface, that is mu naught I upon 2 pi R, right? But after, when you're going outside the surface, your radius will be greater than R. So as your radius increases, so your magnetic field will be decreases. Yes or no? Increasing the radius, magnetic field will be decreases as it is inversely proportional. So there is variation you see here. As you increasing the radius, magnetic field will be decreasing. See, yes. On increasing the radius, magnetic field will be decreasing. Yes or no? So this is the variation of first type when you having metallic cylinder. But when current is threading all over the area, second case, okay? So for first case, we derived that current for metallic conductor, current is only flowing on the surface. But second case, when current is threading all over the area. Yes. See here. Second case. If the current is uniformly distributed throughout the cross section, okay, then what happened? See, inside the cross-sectional area, we have derived B is proportional to R. As we have the derivation like this, mu naught I upon 2 pi R square into R. So this whole is a constant. This was the relation for B. So B is proportional to R. Yes or no? Yes. So for R is less than R, B is proportional to R. So what type of variation is there? See here in this diagram. So this is complete radius R for this point. But when you are inside this whole radius, cross-sectional radius, then the derivation was this B is proportional to R. Okay? Check the variation and try to understand it completely. Yes, this vector representing the B, amount of B, and this side is about the for the radius. So up to this periphery, a small r becomes capital R. The variation of magnetic field is like this, proportional. B is proportional to a small r. Okay, so it is the direct variation. Clear or not clear? So inside the radius for given conductor, B is equals to mu naught. What I have derived here, check here once again. Mu naught I upon 2 pi r square into r. Mu naught I is I upon 2 pi r square. This whole as a constant into smaller, right? And on the circumference, it is B maximum at BR. So BR, it was mu naught I upon 2 pi capital R. Clear? But again, after when you are moving outside your cylinder, so B is inversely proportional to R. Clear? Because whenever small r is greater than R, you equal to B equals to mu naught I upon 2 pi is small r. So B is inversely proportional to R. Clear or not clear? Check here. Yes, inside up to the circumference, B is directly proportional to R. B at R, capital R will be maximum and it is inversely proportional to R. Okay. So where the magnetic field will be maximum? On the surface. Yes, you check here. This is the maximum value of magnetic field. Where? When a small r, the radius of the loop equal to radius of the conductor on the surface. Yes or no? On the surface. So that is why on the surface the magnetic field will be maximum. Clear? So the magnetic field is maximum for a point on the surface of a solid cylinder. So this was the question of last year, 2025. Optional questions is there. Okay, at which point the magnetic field due to a current carrying conductor will be maximum? Inside the conductor, outside the conductor, on the surface? None of these. So it is on the surface. Clear? And for a on the surface of solid cylinder carrying current, and it is zero for a point on its axis of cylinder. Yes, remember, and it is equal to zero on the axis, it will equal to zero. Why? Because B is proportional to R. Check here. What we have, find the value of B for any type of cylinder. It is equals to mu naught I upon 2 pi R square. Sorry, capital S square into R. So your loop radius is taken from the axis of cylinder, and when your point is lying on the axis, then you have no radius of this one because your point is lying on the center line. So this means on the axis r becomes 0. Yes or no? So if you place here r equal to 0, then b equal to mu naught I upon 2 pi r square, and the value of r equal to 0. Why, my dear? Because your point is lying on the axis. Okay. So on the axis, there is no radius. So all total, it is equal to 0. Clear or not clear? Check here. This one point, what is here? Here r equal to 0. Slowly, slowly, r is moving up to the r. So whenever r equal to 0, b is also 0. Okay. So at r equal to 0, b equal to 0. Okay. In simple word, on the axis of a current carrying cylinder, your intensity will be always 0. Right? Okay, guys. So moving to the next topic. Next topic is Ampere's law, using Ampere's law and its application for a straight solenoid, only qualitative treatment. Yes. So next, solenoid. So a solenoid consists of an insulating long wire closely wound in the form of a helix. It is a length very large and as compared to its diameter. Means the diameter of the solenoid is very small. Okay. With comparison to its length, the diameter is very small. Right. So this is the field in a solenoid. Like here, the current is going inside. Okay. And current is coming outside. See, so this is the north pole. Here it is north pole, and this one is south pole, and the solenoid behaving like a bar magnet, right? Yes. Yes, see here. This way, the current is from this thread, from this loop, current is getting downward, and here the current is inside. So this is north pole. Why? Because the current here is like this. See here is like this. Okay. So it is anti-clockwise. Here it is the current is sorry. North. Yes. Here the current is anti-clockwise. See here. here it is anti-clockwise. So the anti-clockwise loop will give you north pole, and here it is clockwise, so it will give you south pole. Okay, anti-clockwise, yes. The rotation, if the rotation of current is anti-clockwise, there will is a rise of north pole, and the rotation of current is clockwise, then there will be a south pole. Understood? So from north pole, the field will be emerges out, and south pole, it will be continue inside the solenoid. Right? Any problem? So magnetic field due to a solenoid. Consider a long straight solenoid, circular cross section. Each two turns of the solenoid are insulated from each other. When current is passed through the solenoid, then each term of the solenoid can considered as a circular loop carrying current, and thus will be producing a magnetic field. The total magnetic field is the vector sum of all the magnetic field due to currents through all the turns in the solenoid. At a point outside the solenoid, the magnetic field due to neighboring loops opposes each other. At a point inside the solenoid, the magnetic field are in the same direction. Yes, see here, this line is more important. Yes, outside the solenoid, the magnetic field are opposing each other. Yes, at a point outside the solenoid, the magnetic field due to neighboring loops opposes each other. Yes, so the magnetic field outside the magnet solenoid is equal to 0. Clear? Because the neighboring field will opposing each other. But this case is valid only for ideal solenoid. Okay, for ideal solenoid this case is valid, and the magnetic fields but inside the solenoid magnetic field is uniform, and all the field lines will be in the same direction. Clear? As a result of it, effective magnetic field outside the solenoid becomes weak, and ideally it is 0. And whereas the magnetic field inside the solenoid becomes very strong and uniform, acting along the axis of the solenoid. Yes. So the direction of magnetic field is parallel to the axis of solenoid. Clear? Yes. When the solenoid is more and more tightly packed, yes. So it is mm, most likely said to be ideal solenoid. The magnetic field due to current through the solenoid will become 0. As I said, the case is more likely to be ideal solenoid at a point outside the solenoid, and it is strong and uniform in the field in the point inside the solenoid. Okay. So here we are only considering ideal solenoid. Let n be the number of turns per unit length of the solenoid, and I be the current flowing through the solenoid, and the turns of the solenoid are closely packed. This means we are discussing here the case of ideal solenoid. Okay. Okay. Now remember one thing. Suppose the length of the solenoid, an ideal solenoid, equals to L. So this is the length of ideal solenoid. Clear? And total number of turns equals to N. So if L length contributing capital N terms, then unit length will contributing N by L tons. Yes or no? So this is number of tons per unit length, and it is said small n equals to number of tons per unit length. Right? Now, so this is a solenoid, and here it is a solenoid like this. Try to understand. Yes. Current is coming outward from this loop. Yes. Here the current is getting outward, and from here current is going inward. Clear? So this is dotted means current going outward, coming outward, and from cross field current is going downward. You see here, upside finger current is coming outward, and here it is downward. Okay, understood clearly? Okay. Now consider a rectangular Amperian loop. So you have given a solenoid here. You have given a solenoid. So what you have to do, you have to consider an Amperian loop. You have considered an Amperian loop. Consider a rectangular Amperian loop of PQRS near the middle of the solenoid. So you have taken a loop PQRS. Check here. This is PQRS. R, and S. Okay. You know the solenoid is ideal, then field is only inside the axis of the solenoid. Okay. Outside this field equal to 0. Now the magnetic field along the path PQ is B and 0 along RS. Yes. On the RS outside the solenoid B equal to 0. Clear beta? Yes. Let the magnetic field along the path PQ be B and 0 along the RS as the path QR and SP are perpendicular to axis of the solenoid. Now, if you talking about the direction of here DL, because this is Amperian loop, so this is the length of the loop like this along this, and here the direction of magnetic field is here. So this angle equals to how much? 90 degree, right? And this angle is also how much? 90 degree. Clear? Okay. The magnetic field component so are perpendicular to the axis of solenoid. So the magnetic component along these path will be 0. Okay. Now the number of turns in the length L equals to NL. Yes, we just talked this. N equals to capital N upon L. So total number of terms equal to N into L. Yes or no? Okay. So now apply the Ampere circuital law for this loop. Okay, beta? We are going to apply the Ampere circuital law. Check here. First, we are starting from PQ. Okay. So for PQ, B dot DL. Okay, beta? So B dot DL for PQ. This is for PQ. B dot DL, P to Q. It is written like this, B dot DL. And we have to incorporate the Ampere circuital law for the whole loop PQRS. So P to Q, Q to R, R to S, and S to P, right? So for PQ, if you open, it will be BDL cos 0. BDL cos 0, right? Because magnetic field is in direction of the loop, right or wrong? Yes, magnetic field here in the direction of loop because magnetic field propagating in the same way along the loop. So B dot dl is here. Now in next one loop, upper one loop, the magnetic field is perpendicular, so cos 90 is here, right? Yes or no? Outside here it is again B dot dl, but remember outside the loop B equal to 0. Yes, check here, outside the loop B equal to 0, outside the solenoid B equal to 0. Agree? And again for the fourth one limb, it is said to be limb. Fourth one limb, fourth one edge, it is equals to angle equal to 90 degree. Again cos 90, right? So cos 90 equal to 0, yes, cos 90 equal to 0. So in this part equal to 0, because of B outside 0, is this part equal to 0 and this part equal to 0. So only it will give B dot dl cos 0 and cos 0 equal to 1. So this will give B into dl. Yes or no? Only B into dl will be left there. So B is constant, take it outside. And integration of dl for this case equals to capital L. Yes or no? Why? Because you have taken the length of this loop is equals to L. Okay. So B into L. Right? B into L. So this is what? This is magnetic field integration, line integration B dot dl. Now this B into dl equals to mu naught into I. Okay, mu naught into I, right? But there are n tons, capital N tons. So you can write the total current equals to, for 1 ton there is I current. So for n number of tons, there will be current of capital Ni. Agree or not agree? For 1 tons there is a single current I. So for capital N tons there is Ni. Okay. So B into L equals to mu naught capital N I. Okay. Yes. Yes. N for singleton there is I current. For the capital N tons there will be Ni current. And student, see here, we have calculated the total B dot dl integration equals to BL, and by the Ampere circuital law, B dot L equals to mu naught multiplied by total I enclosed. Okay, we have to find the I enclosed. What is the amount of total current? Okay, we need to find the total amount of current. Check there. In a unit length, then there is a small n turns. Yes, in unit length. In a unit length, how many number of turns are there? A small n, right? So in total length, total length, how many terms will be there? Capital L, sorry, n into L, right? Otherwise, small n is taken as capital N divided by L. So from here, the total number of terms equals to a small n into L, right? These are what? Total number of terms. Understood or not? Yes. So these are total number of terms. If one term containing I current, then NL terms containing total enclosed current as N into L into I. Yes or no? Because the number of turns equals to a small nl. As the number of turns are a small nl and one thread carrying a current of I, so NL thread will carrying a current of NLI. Okay. So the amount of total current I enclosed equals to B into L equal to mu naught multiplied by NLI. Okay. L say L cancel L to L. Now B equals to mu naught Ni. So this is the magnetic field inside the current carrying coil. Yes, solenoid. B equals to mu naught Ni. Right? If you want, you can place the value of a small n, that is equals to capital N by L. So it is equals to mu naught Ni upon L. Done. Clear? So this is the magnetic field inside a solenoid. And remember, outside the solenoid, at the corner of the solenoid, you can say near a point at the end of solenoid, the magnetic field is just half of the at the center, that is mu naught Ni by 2, right? Yes, the linear solenoid carrying current is equivalent to a bar magnet. Yes, solenoid is like a bar magnet. This pole is giving north, this pole is giving south. Done. So check here, total number of terms. So as number of turns per unit length, that is equals to total number of turn upon in n length equals to n by L, capital N by L. So from here, capital N equals to small n into L. Now, so the total number of terms equals to small nl. Now there are number of terms, capital N number of terms, and each term containing a current I. So we want total amount of current actually. So I enclosed from that loop. So I enclosed equals to how much? Total number of turn multiplied by current. Current through one term multiplied by total number of current. So it will become I into NL. So it is equals to NIL, right? Now we have B dot DL. B dot DL we find as B into L. So B dot dl is equals to mu naught Ni. By the Ampere circuital law, B dot dl equals to mu naught into I enclosed. So B dot dl is as BL, and here it is mu naught NIL. L to L cancelled, and finally B equal to mu naught Ni. This is derivation. Done.